solve linear ODEs, right? We have several, 2 or 3 different analytic techniques. So the Laplace transform is just another one. So why bother, right? You asked me this last class. So it turns out that the Laplace transform is pretty good at handling differential equations that contain a discontinuous function, which none of our other techniques can handle. So discontinuous functions are used to model all kinds of real phenomenon, like turning a switch on and off. Okay? Like, so you could have a function that's 0 and 1, which is called the Heaviside function. Heaviside was an engineer. That was his name. Yeah, it's a person. So it makes you, it kind of goes because you have 0 and 1, and so one side's heavy, but it's really a name. It doesn't mean that. So the Heaviside function is just this piecewise function. It's 0 for t is less than some number a, and 1 for numbers bigger than or equal to some number a. Okay, so we denote that u sub a, and a is just the cutoff point where you switch from 0 to 1. So this can model like a light switch. Turning it off would be 0, on would be 1. All right, so what I want to do is I want to take the Laplace transform of this function. So we have to remember what the Laplace transform is. I'm just going to use the definition. So the Laplace transform of the Heaviside function, that's just the integral from 0 to infinity of the Heaviside function times e to the negative st dt. Definition of the Laplace transform. All right, but u sub a is defined differently from 0 to a than it is from a to infinity. So I'm going to break this integral up into 2 integrals. The integral from 0 to a of u sub a of t e to the negative st dt, plus the integral from a to infinity. So that's just a property of integrals that you learned in Calc 2, that you can break a function up into 2 integrals. Sorry, break an integral up into 2 integrals. All right, from 0 to a, the Heaviside function is 0, right? So this is just 0 times e to the negative st dt, and the integral from 0 to a of 0 would be 0. So this first piece is just 0. The integral from a to infinity. Now from a onwards, for t is bigger than or equal to a, u sub a is just 1. So this is just the integral of e to the negative st dt. Okay, so this becomes, take the antiderivative of e to the negative st, so we get e to the negative st over negative s. And I have to evaluate that from a to infinity. But the way you do that evaluation is you have to take a limit. This is the limit as b goes to infinity times e to the negative st over negative s, evaluated from a to b. And we're just going to let b go to infinity. So evaluated from a to b, that means plug in the b, plug in the a, subtract the 2, and then we'll take the limit after we've done our plugging in. So this is the limit as b goes to infinity of e to the negative bs over negative s minus e to the negative as over negative s. And then we let b go to infinity. So that was just plugging in b, plugging in a, subtracting, evaluating the function from a to b. And then we let b go to infinity. And what happens to this first term? Goes to 0 because b is getting bigger. So we have e to the negative something. So this goes to 0. And this doesn't change at all because there are no b's in it. So this is 0 minus a negative. So I end up with positive e to the negative as over s. So that's the Laplace transform of the Heaviside function, u sub a. So we can split it anywhere now. We could let a be any number, and we now know the Laplace transform. So just to write down, we now know the Laplace transform of u sub a of t is e to the negative as over s. Nope, I didn't. The e came from the definition of the Laplace transform, where you multiply the function, which is just u sub a, times e to the negative st. All right, so now we can take the Laplace transform of any Heaviside function. 0 for some values, 1 for other values, and we can split where 0 is and where 1 is anywhere. All right, so now we're going to use this, a fact that we know how to do this Laplace transform, to solve an initial value problem. So I have y prime equals negative y plus u3 of t. So that's just a Heaviside function, 0 when I'm less than 3 and 1 when I'm bigger than or equal to 3. And I have an initial value. But before I start trying to solve it, I'm going to solve it with a Laplace transform. But before I do, I just want to do a little qualitative analysis. Because it's an autonomous differential equation, I can get its slope field. So I could rewrite this differential equation as negative y. So when t is less than 3, u sub 3 is 0. So this just says negative y plus 0. And when t is bigger than or equal to 3, it's negative y plus 1. So this is really a piecewise differential equation. And I can get the slope field by plugging in to this equation when t is less than 3 and to this equation when t is greater than or equal to 3. So I've got my slope field and I have my function. So now that I have sort of a qualitative picture of the solution, I can compare that to my analytic solution when I finish. See if it makes sense. All right, so we want to solve the initial value problem using a Laplace transform. All right, so when you have a Laplace, when you're going to use a Laplace transform to solve a differential equation, you start by taking the Laplace transform of both sides. So I take the Laplace transform of y prime, and that should equal the Laplace transform of negative y plus u3 of t. And then last class, we learned how we derived a formula for taking the Laplace transform of a derivative of dy dt. And that is always going to be s times the Laplace transform of y minus y of 0. And then I can use the linearity of the Laplace transform to pull the negative outside here. So I'm going to have negative the Laplace transform of y plus the Laplace transform of u3 of t. So you can take the Laplace transform of each piece separately, and any constants you can pull out in front of the Laplace. All right, so I can plug in my initial value. So replace y of 0 with a 2. And the Laplace transform of u3, we just learned how to calculate for any particular u sub a, and it was e to the negative as over s, and in this case a is 3. So e to the negative 3s over s. Okay, so now I just have to solve for the Laplace transform of y. Gather them all on one side, factor out the Laplace transform of y, and divide by the coefficient. You could write it as 1 over s times e to the positive 3s, yeah. So we add the Laplace transform of y to both sides. We add 2 to both sides. Factor out a Laplace transform of y. And I have s plus 1. Then divide both sides by s plus 1. So we've got the Laplace transform of y equals 2 over s plus 1 plus e to the negative 3s over s times s plus 1. So at this point, last class, we had to do some, we only know one Laplace transform, right? So I have to figure out a function y whose Laplace transform is this thing, right? The 2 over s plus 1 I can do because I only know functions whose Laplace transform looks like 1 over s minus a. Right now, those are the only kinds that I know. So I can do the first one. I would say y is the inverse Laplace transform of the right side here. And then I can take the inverse Laplace transform of each thing separately. I pulled out the 2, yep. Okay, so now this first inverse Laplace transform I know. From last class, I know that that has to be what function? 2e to the negative t. Yeah. So I've got the 2 in front here. That comes along. This is 2. And then the function whose Laplace transform is 1 over s plus 1 is e to the negative t. So this is 2e to the negative t. And then the inverse Laplace transform of this mess, we don't know how to do right now. All right, so we're a little bit stuck. We're going to have to figure out how to do that, and then we'll come back to this. Everybody have this? Okay. All right. Okay, so in order to finish this initial value problem, we have an inverse Laplace transform to deal with that we don't know how to right now. So here's the little trick. Okay, so Heaviside functions are a useful way to shift a function to the origin. So I'd like a function g of t that's going to be exactly the same as f of t, but shifted, so that time t equals 0 for f corresponds to some future time t equals a for g. So I'm just trying to come up with a new function g that's a horizontal shift of f. So for time t less than a, g of t is going to be 0. It just doesn't exist. Okay. T equals a is going to be corresponding to t equals 0 for f, and before that doesn't exist. So here's an efficient way to write a function g that does this. G of t is going to be u sub a of t, the Heaviside function, times f of t minus a. Okay, so f of t minus a is going to cause my horizontal shift to go right a units. But then u sub a of t is like a switch. this is going to be 0 when we're less than a, and when t equals a, it's going to turn this on. It'll be f of 0, yeah. Yeah, so let's, g of a, right, is going to be u sub a of a times f of a minus a, which is 0. And when t equals a, the Heaviside function is 1. So this is 1 times f of 0, which is f of 0. So this is exactly what I want. I want g of a to correspond to f of 0, because g of t is supposed to be a shift a units to the right of f of t. So that gives us exactly what we want there. And if I were to do, say, g of b, where b is some time after t equals a, this is going to be u sub a of b times f of a plus b minus a is b. Plugging in t equals a plus b. I meant to do a plus b, sorry. So I'm just doing some future time after a, after t equals a. So u sub a of a plus b would be 1, because b is just some positive value. And this is going to be 1 times f of b, which is f of b. So you see that g is, again, this is just a horizontal shift of f. All right, so this is a nice handy way of just shifting a function to the right. And having a switch, it makes the function not exist before time t equals a. So here's an example. So I graphed a couple. So this is the function e to the negative t. I can shift it 3 to the right by taking e to the negative t minus 3, right? So this is just, you know, a college algebra style problem. How do you shift this 3 to the right? You would subtract 3 from the input of t. But I also want it so that it does not exist before this point here. I want this all to be 0. I don't want to just take this continuous function and shift it to the right 3. I don't want any of this stuff to exist after I shift it. So I use the u function to make it 0 before that. All right, so that was a little detour. Let's take the Laplace transform of this g of t function. That's a shift of f. So remember, g of t is u sub a of t times f of t minus a. So g of t is just this interesting way of shifting f and making it not exist for t's less than a. So I want the Laplace transform of g. So I use the definition. The Laplace transform is the integral from 0 to infinity of your function times e to the negative st dt. All right, from 0 to a, g of t is just the 0 function, because u sub a of t is going to be 0. 0 times anything is 0. So from 0 to a, this integral is 0. And then I'm going to add the integral from a to infinity. And this first integral is going to be 0. All right, and g of t, when t is bigger than a, is just f of t minus a, because u of t is just 1. So instead of g of t, I'm going to write f of t minus a. It's 1 times f of t minus a. All right, so now I have a composition. I'm taking an integral of a composition there. T minus a is the inside function. What technique do you use on integrals that are compositions? U substitution. By parts is for multiplication. Yeah. All right, so I'm going to let u be the inside function, t minus a, which means that du dt is 1, so du equals dt. And when you do u substitution, one of the techniques that we used was to change the bounds on the integral using u. Sometimes we would do the whole thing and then change the variables back before we evaluated. But one little shortcut you can do is change the bounds. So my lower bound is a, u of a is 0. You plug an a in for t. In this function, u equals t minus a, if t equals a, u equals 0. Yeah. So when t equals a, u equals 0. So I'm going to replace this bound of a here because I'm changing all my variables to u's. This a is a t value. I'm going to replace it with the u value of 0. The other one stays infinity because this is still an increasing function. So as t goes to infinity, u goes to infinity. All right, so this has become the integral from 0 to infinity. Instead of f of t minus a, I'm going to have f of u. And then I'm going to have e to the negative s. And instead of a t, I'm going to put a u plus a, right? This equation that relates u and t. If u equals t minus a, then t equals u plus a. And then replace dt with du because dt equals du. All right, when you distribute this negative s to your u plus a, you end up with e to the negative su minus sa. I'll write it all out. Integral from 0 to infinity, f of u times e to the negative su minus sa. And then I can do my little trick that we use all the time. This is e to the negative su times e to the negative sa. And e to the negative sa is just a constant, okay, because my variable is u. So I can pull that right out of my integral. Right. Well, yes, we don't have a way to integrate this, but we should recognize this. The integral from 0 to infinity of f of u times e to the negative su, that's the Laplace transform of f. Right? Usually we write it with t as the input variable, but it's just the name of the variable. So this is e to the negative sa times the Laplace transform of f. So that's a big conclusion. Yeah, I'll write it down. So, well, I'll let people finish writing this down. That was a lot of stuff. Yeah. Okay, so the conclusion is, if you know the Laplace transform of f, oops. If you know the Laplace transform of f is some function of s, right? If you can do the Laplace transform of f, then the Laplace transform of the product of u sub a of t times f of t minus a, which is just a horizontal shift of the function f, okay, is going to be e to the negative as times f of s, the Laplace transform of f. Okay, so if you know the Laplace transform of f, you can find the Laplace transform of a horizontal shift of f. So if we use this formula for a particular example, the one that I actually showed you the graph for, right, so I'm going to write the formula down again. The Laplace transform of u sub a of t times f of t minus a Okay, so if I want the Laplace transform of this function, in this case, a is 3, and my function f is e to the negative t. So I want the Laplace transform of u sub 3 of t times e to the negative t minus 3. So my a is 3, t minus 3 is my shift. So my function that was shifted was e to the negative t. So this is going to be e to the negative 3s, just replace the a with a 3, and times the Laplace transform of e to the negative t, the parent function that was shifted. And I get e to the negative 3s times 1 over s plus 1, okay, because we know how to take the Laplace transform of exponentials from last class. And so we just multiply these, and we have e to the negative 3s over s plus 1. Yeah, it just makes the thing that you're taking the Laplace transform of easier. Okay, so what's the point? How does this help us solve the initial value problem? This guy was one of the functions that we needed the inverse Laplace transform of. So now I can pull this out. Or it looked almost like this. We might have to do a little manipulation, but the thing that we needed the inverse Laplace transform of that we didn't know how to get looks something like this. So let's go back to that. We had left off right here. I said y equals 2e to the negative t plus the inverse Laplace transform of e to the negative 3s over s times s plus 1. And that second inverse Laplace transform we didn't know how to do. But now we can look at that and say that looks very much like the Laplace transform of a horizontal shift of e to the negative t, which we know how to do. But it's not quite right because my denominator isn't just s plus 1, it's s times s plus 1. So how could I break it up? Partial fractions. So I'm going to just go ahead and do that. Or I did it on my paper. You can do it on your own at some point. So we're going to get e to the negative 3s over s minus e to the negative 3s over s plus 1. S plus 1, and I got 1 and negative 1. Yeah. So from here to here, partial fractions. Yeah, I don't need to because No, so I can't just pull it out because s is my variable, so it's not a constant. When I was doing the integral, u was the variable, so I could think something with s out, but in this case, it's the variable. Right, right, exactly. Yeah, so right here, I can separate these into two Laplace transforms. So this is going to be plus the inverse Laplace transform of e to the negative 3s over s minus the inverse Laplace transform of e to the negative 3s over s plus 1. Now, I use what we were just working on. We were taking the inverse Laplace transform of a horizontal shift of an easy function, and we were coming out with things that look like this, right? And this one was actually exactly what we got, right? When we took the inverse Laplace transform of the Heaviside function times a horizontal shift of f, which is e to the negative t. Yeah. So this we already calculated. We know this from a couple slides ago. We found a function whose Laplace transform is e to the negative 3s over s plus 1. It is u sub 3 times e to the negative t minus 3. Okay, what function do you think, could you conjecture, would give you a Laplace transform of e to the negative 3s over s? Close. So this becomes e to the negative t minus 3 because this is s plus 1, right? The s plus 1 tells you the coefficient on e to the t. So let's go back a couple of days. So if I have 1 over s plus 2, right, and I want the inverse Laplace transform, what would that be? E to the negative 2t, right? So it's this number in the denominator that gives you the coefficient on t. E to the 0, yeah. So when there's no number added to the s or subtracted from the s, the coefficient on t is a 0. So the shift doesn't even matter. This is just, yeah. So this is just u3 of t, which is just, well, sometimes it's 0. Right, but this is a function for all t that I'm trying to come up with here. Go ahead. When the denominator is just s, the inverse Laplace will always just be u. And which u, right? U sub 3, that comes from the exponent on my e.
The u sub 3 in the second part, is that u sub 3 of t times e to the
Yes, yes. Yeah. So there is my function. So when t is less than 3, all my u's turn off, right? All my u's are zeros, and I just have 2e to the negative t, which is a decreasing function, right? So let's go back to our slope field. This definitely looks like exponential decay from 0 until as I approach t equals 3. Okay, so I have the first part correct. And then after that, it looks like my function increases and has an asymptote at 1, increasing towards an asymptote of 1. Let's see what the analytic solution tells us. Yeah, so, yep, so U3 is going to be a 1. And then I'm subtracting some kind of exponential decay, something smaller and smaller. So I'm approaching an asymptote of 1. Yeah, you could almost come up with this just by looking at the qualitative behavior. All right, so before I have you try one, I feel like I should give more clarification on how to do the inverse Laplace transform of e to the negative a t. Now let's not call that a. This is e to the negative something t over because that's my a. Nope, this is my a. What should we call this? K. Okay. So if you want to take an inverse Laplace transform of an exponential over s plus k, well, 1 over s plus k we know how to do the Laplace transform of, right? And this is just going to be, this should just come out to e to the negative. Right, it should be u sub a of t times f of t, which is going to, yes, there we go. So yeah, we didn't derive this formula generally. We did an example, and we're generalizing based off an example, which is not good mathematics, but we'll do it for now. Okay, so that should help you when you're trying to do inverse Laplace transforms. Oh, no, oh, sorry, hang on. It's not negative kt, it's negative k times t minus a. It's a transformation. It's the horizontal shift. Yeah, that's it. All right, so now we can, did we finish solving that initial value problem? We did, but I don't know if I did it right. Let me check. Yeah, perfect. Okay, good. All right, so now you have enough info. Try to solve this initial value problem in your groups.